Welcome back to the deep dive. Today, we're reaching the finale of our journey into Aryabhata's work. We'll be focusing tightly on the first 25 verses of his Kālakriyāpāda.
Yeah, this is really the capstone, pulling together everything we've looked at recently. A synthesis, if you will.
Exactly. And just to set the scene again, we're talking 499 CE, Pataliputra, smack in the middle of the Gupta Golden Age.
Right, an incredible time. You've got this amazing intellectual and cultural energy. Think Ujjain's growing astronomical reputation, Nalanda's intense scholarly debates. It's quite the backdrop.
And into this steps Aryabhata, just 23 years old, presenting this system. It's kind of mind-blowing to think how his ideas then connect even distantly to things like how we time Diwali today, or how JPL navigates rovers on Mars.
It really is. That connection across centuries is powerful. It shows the lasting impact of getting those fundamental principles right.
Absolutely. And for listeners who caught our earlier deep dives, maybe episodes 20 to 23, you'll recognize some themes, but you definitely don't need to have heard them to follow along today.
No, not at all. We're aiming for a complete picture right here.
So our mission today is basically to understand Aryabhata's blueprint for time, space, and how the planets move, all based on these crucial opening verses of the Kālakriyāpāda. Ready for one last big dive.
Let's do it. And it's worth remembering the Gupta context itself, a period of really significant advancements. Aryabhata's work, the Aryabhatiya, feels so lean, almost like an algorithm. It really captures that spirit of precision.
Okay, let's start to unpack that vision. His approach feels very mathematical, very observational. He's building this cosmic system with numbers, with cycles. It feels quite practical, especially maybe compared to later views that brought in more divinity. I think Bhaskara came up.
That's a really good point. While people like Bhaskara definitely have built on Aryabhata, they did sometimes weave in more, let's say, philosophical or theological layers.
Okay.
But Aryabhata, here in the Kālakriyāpāda, he's laying down this framework that's strikingly mathematical. Observational. This is the bedrock.
The operating system, like you said.
Pretty much, yeah. It's the foundation for everything else he calculates about the heavens.
Okay, so it's his cosmic instruction manual. Let's get into the details, starting with how he defines time in those very first verses.
Right, verse 1. He immediately lays out the hierarchy. A year is 12 months. A month, 30 days. A day gets divided into 60 knots.
Okay.
And then each notch is split into 60 vināḍikās. It's about establishing this consistent, mathematically neat system for measurement.
60 seems to be a key number there. Now, notch, vināḍikās, we've bumped into these before. Can we translate them into, like, minutes and seconds for us?
We can. Roughly speaking, a notch is about 24 of our minutes.
24 minutes, okay.
And a vināḍika works out to around 24 seconds.
Wow.
And think about the practical use. You could schedule harvests, time religious chants for specific star positions, record observations. These weren't just abstract units. They were woven into daily life, connecting earthly activities to cosmic rhythms.
That really paints a picture, doesn't it? Using these precise timings for everything from farming to astronomy. Then verse 2, that connects it right down to the human level.
Exactly. Verse 2 makes this incredible link. It says, one sidereal vīnika, that's about 24 seconds, remember, is equal to the time it takes to pronounce 60 long syllables, or roughly 6 breaths.
6 breaths. So our own breathing becomes a unit of cosmic time.
Precisely. It connects the microcosm of human life to the macrocosm. He then says, just as time is divided this way, so is space, the celestial sphere's rotation. It's beautiful, that sense of interconnectedness.
That's amazing. Our breath as a cosmic metronome. So how does he scale that up to, say, the Earth's rotation?
Well, he calculates that a full sidereal day star returning to the same spot contains 21,600 breaths.
21,600, okay.
And that number, 21,600, is directly related to the 360 degrees in a circle. It works out that for every 6 breaths, or 1 vīnika, the Earth turns 1 minute of arc.
Wow, that's elegant.
It really is a direct link between breath and angular rotation. It makes you think in a very different way about modern GPS. That relies on hyper-accurate atomic clocks measuring signal travel time to pinpoint location.
Right.
Both systems, Aryabhata's and GPS, fundamentally hinge on precise timekeeping to understand position and movement, just vastly different scales and technologies.
That's a fantastic parallel. From breaths to atomic clocks. It hammers home how crucial time measurement is. Okay, then verse 5 introduces different kinds of days and years. This sounds like it could get complicated.
It's definitely a key verse for understanding his calendar. He defines 4 types: Solar years, based on the sun's apparent path.
Okay.
Lunar months, based on the moon's phases, specifically sun-moon conjunctions. Civil days are standard sunrise to sunrise day. And sidereal days, Earth's rotation relative to the stars.
Got it. And he mentions Lanka as the reference point. It sounds like they're Greenwich.
Exactly. Lanka, often placed conceptually on the equator in ancient Indian thought, was his prime meridian. Sunrise there was the 0 point for time and longitude calculations, and his system, the Ahargancha, this continuous day count, it cleverly includes rules for adding leap months and sometimes skipping lunar days to keep the solar and lunar calendars synced up. It's needed for festivals to land in the right seasons.
Yeah.
Think about NASA mission planning. They need incredibly complex calculations to sync spacecraft maneuvers with planetary alignments and seasons. It's that same fundamental challenge of synchronizing different cycles.
Right, keeping all the cosmic clocks ticking together. So moving from daily and yearly cycles, verses 8 to 11 take a massive leap outwards, right, to the Kalpa.
Oh, huge leap. Verse 8 defines the Kalpa, a day of Brahma, as 1,000 yugas. And we've talked about yugas before, fitting into a Mahayuga.
Yeah.
A Kalpa totals, get this, 4.32 billion years.
4.3 billion, that's immense, older than the Earth itself.
It is, and he says the night of Brahma is equally long, making the full cycle 8.64 billion years. It just shows the staggering time scales these ancient thinkers were grappling with.
Mind-boggling. We mentioned the Mahayuga before, the 4.32 million year cycle. So the Kalpa is 1,000 of those. And didn't Aryabhata have a unique take on the yugas within that cycle? Something about them being equal?
Yes, that's a very important point. Unlike other models where the yugas Krita, Treta, Dvapara, Kali represent a decline, getting shorter and morally worse, Aryabhata proposed they were all of equal length. This suggests a more purely cyclical view, perhaps less focused on moral decay and more on mathematical regularity, a significant departure.
Interesting. Less about cosmic decline, more about repeating patterns. So after those vast timescales, verses 9 to 11 bring us back to something more usable, a starting point for calculations.
Exactly. He sets the beginning of the current Kali Yuga 3102 BCE in his system as the epoch, the 0 point for all his time calculations.
Okay, the anchor.
From that anchor, he explains how to calculate the daily positions of planets from sunrise at Lanka, and crucially, how to apply corrections for the various irregularities in their motion. It's very much like how modern astronomy software works. Start with initial conditions at a known time, then apply calculations continuously to predict future positions.
So set the master clock, then keep making fine adjustments.
Ah.
Got it. Okay, let's shift gears from time to the planets themselves. Verses 12 to 16 start mapping out their dance.
Right. Verse 12 introduces a kind of baseline idea. All planets, from the moon out to Saturn, complete their orbits in 60 solar years by divine measure, and initially, he treats their motion as uniform.
Uniform, like they all move at the same speed.
Well, Bhaskara, I interpreted this later as meaning a consistent daily movement of 11,800 yojanas. That's a Gupta unit of distance for all of them. It's a simplification to start with, before getting into the complexities.
Okay, like a first approximation. It's a neat image, though all celestial bodies keeping the same tempo, even on different sized tracks.
It is. But verse 13 immediately adds the nuance. He clearly states the relationship between orbital size and period. The moon is closest, moves fastest, orbits in about 27 days.
Right.
Saturn is farthest, moves slowest, takes about 30 years. This observation, this inverse relationship, conceptually echoes what Kepler later formalized mathematically, even though Aryabhata is working with an Earth-centered model.
So he's capturing that fundamental relationship even within a different cosmic structure. What about verse 14, the angular divisions?
This one's clever. He says, even though the orbits are vastly different sizes, the way we measure angles along them degrees, minutes is the same for all.
Ah, okay.
So 30 degrees of the moon's tiny orbit is a much shorter distance than 30 degrees of Saturn's huge orbit, but angularly, it's the same measure. It gives a universal grid for plotting positions.
Like latitude and longitude on the celestial sphere. Makes sense.
Exactly. Think Google Maps scaling the coordinates stay consistent even as you zoom in or out.
Gotcha. Then verse 15 spells out his actual model of the cosmos, the geocentric layout.
Yes, this is crucial. Earth is at the center. Then comes the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and then the stars beyond.
And the order is based on?
Primarily on their observed speeds and orbital periods as seen from Earth. Slower objects are placed further away. And we have to appreciate, while we know it's heliocentric now, This geocentric model was incredibly sophisticated for its time. It allowed for remarkably accurate predictions.
Right.
The kind of precision needed reminds me, again, of JPL planning rover paths. Different model, but the same need for detailed, accurate calculation based on observation.
A functional map, even if not the correct map by our standards.
Yeah.
Okay, verse 16 introduces anomaly points. This sounds like where we get beyond simple uniform motion.
Exactly. This is the key. To get the true motion, you need to account for anomalies. These aren't places, but mathematical points in his model that help explain why planets don't seem to move at a perfectly constant speed from our perspective. These anomalies are what necessitate the corrections he details next.
Right, which takes us into the real computational heart of it, the cosmic code. Verses 17 to 24. This is where the math gets serious.
Pretty much. Verse 17 introduces the two main types of corrections. Manda, meaning slow, and shigra, meaning fast.
Okay, slow and fast corrections, what do they do?
The Manda correction adjusts for the planet appearing to speed up when closer to Earth and slow down when farther away. Think apogee and perigee, roughly.
Like adjusting the tempo.
Exactly. The shigra correction is used primarily for the outer planets and Venus, Mercury to explain things like retrograde motion when Mars seems to loop backwards in the sky.
The DJ scratching effect. And this is where things like epicycles might come in conceptually. Planets on circles on circles.
Well, Aryabhata doesn't explicitly say epicycle here, but the shigra mechanism functions very similarly, and later commentators definitely drew that connection. Verses 18 and 19 then show how to calculate these.
Okay, the math bit.
Yeah, he uses the sine and cosine of the anomaly angle, basically, where the planet is relative to its anomaly point. These trig functions, which were quite advanced in India then, are scaled by orbital factors for each planet to figure out the exact adjustment needed for its daily motion.
So, sine waves to tune the planet's movements, like tuning instruments in that cosmic orchestra we imagined.
That's a great analogy. It's about using these mathematical tools to achieve that celestial harmony and predictive accuracy.
It's just incredible they were using sines and cosines for this back then. But wait, verse 20 adds another twist. These anomaly points aren't fixed.
Nope. Another layer of complexity. Verse 20 points out that the apogees, the fast points, even the moon's nodes where its orbit crosses the sun's path, they all shift slowly over time.
Wow. So the planets are following paths that are themselves subtly changing.
Exactly. It's not a static clockwork, it's dynamic. Think of your GPS rerouting not just for traffic, but because the roads themselves are slowly being rebuilt over decades. It requires constant updating.
A constantly evolving cosmic dance. So, verse 21 connects the anomaly angle to whether you add or subtract these corrections.
Precisely. Depending on the angle's value, the correction might be positive, speed up, or negative, slow down. This is how the model reproduces those observed effects: Mars looping, Venus oscillating back and forth near the sun. These calculations would be constantly checked against observations, like NASA using star trackers today to verify spacecraft positioning.
Observation feeding back into the model. Makes sense. Verse 22 then has a specific technique for the outer planets, something about half corrections.
Yes. For Saturn, Jupiter, and Mars, he suggests applying only half the Manda and Shigra corrections first, then the other half. It's likely a numerical method to avoid overshooting the mark, to ensure stability in the calculation.
Like damping the calculation to prevent errors.
Kind of like that, yeah. Like JPL making small, careful thruster burns instead of one big one. It shows a real sophistication in handling the calculations carefully.
Very nuanced. Okay, verse 23 gets into calculating the actual size of the correction, the difference between where the planet should be and where it really is.
Right, calculating the correction arc. This involves, again, the sine of the anomaly angle, scaled by the size of the epicycle or equivalent parameter, and then divided by the card, the true Earth-planet distance at that moment, basically the hypotenuse in his geometric model.
More trigonometry.
Absolutely. It highlights how central Gupta-era trig was to achieving this precision. It's like using Photoshop's sharpening algorithms, complex math under the hood to get a precise visual result.
Using triangles to map the heavens. Amazing.
Oh.
And verse 24, it sounds like maybe a shortcut.
That seems to be the case. It offers a potentially quicker, maybe less computationally intensive way to estimate the Shigra correction using the sign of the difference between the mean and true positions.
Like a light mode calculation.
Yeah, that's a good way to put it. Faster, maybe good enough for some purposes, but verse 23 is likely the full precision method. It suggests he understood trade-offs between speed and accuracy.
A very practical, almost modern consideration.
Yeah.
Okay, that brings us to the end of that section, verse 25. And thinking about the big picture, Aryabhata's legacy.
Right, verse 25 basically wraps up the Kālakriyāpāda. Aryabhata says, okay, I've covered time, space divisions, the math, the planet motions, and it explicitly sets up the next chapter, the Golapāda.
Which dives into the 3D sphere.
Exactly. The Earth's rotation, the celestial sphere in 3 dimensions. It's like finishing level 1, unlocking level 2, moving from the flat map to the globe.
A perfect transition. And his influence. It just spread outwards, didn't it?
Hugely. In India, astronomers like Lala Bhaskar II, they all built directly on his foundations.
Yeah.
And critically, his work, especially the sine function and algebraic methods, traveled to the Islamic world. That transmission was vital for the development of math and astronomy there, which then flowed into Europe and influenced the scientific revolution. It's a remarkable chain reaction.
And we still see the echoes today.
Absolutely. His explanations for things like retrograde motion were groundbreaking. The mathematical principles have conceptual links to GPS calculations. Predicting lunar cycles for Diwali goes right back to the kind of accurate lunar tracking he systematized.
So the code in JPL systems, or even my phone's map app, has some distant ancestor in 5th century Pataliputra.
In a very real sense, yes. The fundamental mathematical framework for describing and predicting motion in space owes a debt to pioneers like Aryabhata. His great achievement was creating this unified mathematical system linking human time to cosmic mechanics.
It's quite a legacy. So wrapping up this deep dive on the Kālakriyāpāda, we've seen this incredibly detailed system for timekeeping, mapping planetary motion within his model, and using advanced math, especially trig, for prediction.
And it was practical. Calendars, timing rituals, understanding the heavens. It wasn't just theory. That link between his ancient code and our modern tech is just undeniable and frankly inspiring.
It really is. So maybe a final thought for our listeners. Next time you're looking at the night sky, maybe see Mars or Jupiter up there. Just pause for a second. Think about the incredible journey of understanding that allows us to know what you're seeing, a journey that Aryabhata took such giant leaps on, mapping it all out mathematically so long ago.
A great thought, and it perfectly sets up our next deep dive into the Golapāda Aryabhata's take on Earth's spin, celestial sphere, cosmic geometry. It's going to be like a Gupta-era VR tour of the universe.
Looking forward to it. We hope you'll join us then. For now, thank you for diving deep with us into the world of Aryabhata.